coming. Thank you to the organizers for having me talk. It's really an honor. And I will go back to experiment now. And what I want to present is a new method to detect a spin Hall effect that works in metals and also works for antiferromagnetic materials, although in this example is a ferromagnetic signal. Okay? In this context, I don't think I have to go into the importance of spintronics and its potential for the future of low-power devices. Let me just say that spin currents generation, transport, conversion, measurement is at the core of spintronics, and that the spin Hall effect is one of the ways to generate spin currents, okay? And the inverse to, let's say, transform them into charge currents together with other common methods also, like spin injection from a ferromagnet, or spin pumping, again, exciting a ferromagnetic resonance in a ferromagnet coupled with another material. In the case of the spin Hall effect, we have a charge current going in one direction, and the spin accumulates in the perpendicular direction, okay? And this happens also in non-magnetic materials, but they need to have enough spin-orbit coupling, as we have heard already yesterday and this morning. And usually, we quantify the efficiency of this spin separation by an angle that we call the spin Hall angle, and it's simply the ratio between how much the spins deviate from the direction of the charge current. So how much current we need to apply to get an appreciable spin current perpendicular to it. It has, well, there are here much brighter experts than me on this field, but just very briefly say that it has phenomenologically, one can describe it as having different contributions, some happening during scattering, like the skew scattering mechanism or the side jump, and others in between scattering effects, and that the different contributions weight more or less depending on the material and the experimental conditions, okay? And also, this is, the measurements of the spin Hall effect are not easy, and this is reflected in a large scattering of the experimental results measured with different methods and on different samples. Nominally the same, but this is exemplified here with platinum, which is the most commonly measured material. Okay, what are the most typical ways to measure the spin Hall angle or spin Hall efficiency? One of them is spin pumping in a stack of ferromagnetic and non-magnetic material. Another is measuring magnetoresistance, again, in a stack of ferromagnetic and the material we want to study, typically platinum, let's say. Then spin valves or non-local spin valves, when also involving stacks of different materials, different interfaces, and sometimes, well, also the spin diffusion length plays a role. We have to make them very small. So we can already hint from here that one of the possible sources of error or of differences in different measurements are the fact that we always have interfaces. So we not only have to worry about the quality of the material, but also of the other materials and of the interfaces themselves, which can be a large source of defects, as every experimentalist knows. So are there direct approaches possible that we don't have a conversion and then interconversion and different materials involved? And the answer is yes. For example, by optical means, already in 2004, and in semiconductors are a bit easier to measure because they have longer spin diffusion lengths. So let's say that the area affected is larger physically. And in this very nice famous figure here, you can clearly see different sign of spin accumulation, that is of the Kerr rotation in the experiment, on the different edges of a gallium arsenide stripe through which the current was flowing in this direction or this direction. okay? And shortly thereafter, in a slightly different experiment, but also by optical means, the spin Hall effect was detected by measuring the angle-dependent polarization of light emitted by electroluminescence in two ends of a two-dimensional whole gas with spin-orbit coupling in a stack forming a clever coplanar design of PN junction LEDs. So, and this, here the material system is also of the gallium arsenide family, so it's all same family of materials with same order of magnitude of spin diffusion lengths as this one here. What about metals? Metals, as I said, they are harder to measure because the spin diffusion length is much shorter. So it's an effect that vanishes sooner. But on the other hand, they promise very large effects. So they are interesting. Of course, we have to go for them. And it was not until 2017 when improving a lot the experimental conditions in the same sort of experiment like the first one I showed, like these guys, which is magneto-optical Kerr microscopy, where you look at the rotation of the polarization of the reflected light on the sample. So improving a lot the experimental conditions, the group around Gambardella in Zurich, they managed to measure rotations of nanoradians, so the order of nanoradians, and like this, measure the spin accumulation at the edges of platinum and tungsten stripes through which the current was flowing. If you look at the screen, perpendicular to the screen in this case, okay? Now, what can we do with X-rays? I work at a synchrotron, and synchrotrons are sensitive to magnetic, X-rays are sensitive to magnetic moments, so what can we do with, can we do something? What do we need to make this experiment? We need a high sensitivity to moments, 10 to the minus 4 or even lower. We need some sort of spatial resolution because we are dealing with devices. We cannot measure a whole surface of a whole sample. And then if we look closely at the sketch from the previous slide, if you see there is spin accumulation in all the edges, not only in the lateral ones, also in the surface and the interface. So could we profit of the surface sensitivity of some of the synchrotron-related techniques? And this is where photoemission electron microscopy comes in. So this is the method that I will show today that we have been using for this study. And in X-beam, so in photoemission electron microscopy, we excite the sample with X-rays, but what we detect, what we form the image with are electrons. In fact, very low energy electrons, electrons with energy of the order of a couple of electron volts, which means, and low energy electrons do not travel very far in solids. So we have a very high surface sensitivity because we detect only the electrons that are produced near the surface. This is of the order of 2, 3 nanometers, 4, 5, so this order, nanometers. So of course, we can make an experiment where we detect this signal, but not this one, okay? And like this, we have a larger detecting surface and we don't have to look at a very thin stripe close to the edges, but we can look at a fairly large surface, so this is one possible advantage. Then, if the X-beam microscope is coupled to a synchrotron beamline, we can choose at will the energy with which we want to excite our sample. That means we can excite resonantly the absorption edge of a particular element, okay? So we can address exactly the iron edge, cobalt, whichever. And also, if we can change the circular, in general, the polarization of the light, which we can do in many beamlines, then we can also have access to magnetic contrast. There is a small asymmetry in the absorption of photons with differently polarized, with different polarizations, depending on the relative orientation of the polarization of the light and the magnetization or magnetic moments in the sample. So this is what we will exploit to try to detect spin accumulation, okay? So it's element specific, as I said, because we go to a particular absorption edge. And also, for antiferromagnets, we can use linear polarization, so a related mechanism, but which is done with linear polarization at different angles with respect to the sample. And we can have also a contrast of spin accumulation in antiferromagnetic metals and going to a even in collinear, because since we are element specific, we are addressing one specific sublattice. Okay, so we can, in fact, we can do the experiment at both sublattices separately and see if they are opposite. Okay, all these experiments were done at the CIRCE beamline at the ALBA synchrotron in close to Barcelona. It's the Spanish synchrotron light facility. This is a beamline, obviously, with an X-ray photoemission microscope and soft X-rays, fully variable polarization, high flux and resolution, and a microspot, which we need anyway to have a high photon density for these photon-hungry experiments. So once we have the microscope and we have the photons, what else do we need? We need a way of bringing currents to the sample, so which is not trivial, but possible in PIM. So in PIM, the samples are in ultra-high vacuum and at high voltage. So it's not obvious to apply currents or pulses to them, but it's possible. And here is an example, is the sample holder that we use at this beamline, which has a PCB layer onto which the different contacts, electrodes of the samples are wire bonded. And then still, it's a very difficult effect, very small, tiny signal, so still, at least to start, we need a material that we expect will be highly efficient in spin accumulation, and we need to optimize the experiment to go to the detection limits, to push the detection limits beyond what we normally do, okay? So, for example, with the electrodes design. Regarding the material, we chose copper bismuth, so bismuth doped copper, because it has already shown 10 years ago a very high efficiency in the spin Hall effect. So this is 11% for 0.5% bismuth doping. And in addition, the group around Lucas Perez was able to show a couple of years ago that it is possible to increase quite a lot this bismuth doping up to a few percent by molecular beam epitaxy co-evaporation of copper and bismuth onto a substrate at room temperature. If you increase the temperature to 100 C, there's already segregation, but like this, at room temperature, bismuth really incorporates into the copper lattice, and there is no segregation. And in fact, in the same work, a very high effective spin mixing conductance was measured for this copper bismuth, in this case with 4%, by comparing, by ferromagnetic resonance and comparing the damping of the YIG or YIG with copper bismuth together, and the difference in damping is due to this spin mixing at the interface. So. And also, as Professor Hoffman has shown, it is also good that already in the recent past, a group has shown that it is not impossible to measure spin accumulation in copper. Okay. This is a very different experiment because it's a spin injection from a ferromagnetic material in transmission geometry and so, but at least we know it's the order of the effect is 10 to the minus 5. It's difficult, but not impossible. Okay, so we can design a device that has current flowing in different directions in the same field of view of the microscope, so we can see the contrast, no? We can see regions where the spin accumulation should be opposite, and then we can orient it so that the sensitivity, due to the X-ray incidence, the sensitivity to the expected spin direction is maximal. This we can do, okay? First attempt. What happened? We are working with low energy electrons, and it seems that the local voltage on the surface, the voltage drop to have a current, you need a voltage drop, was creating a background that was orders of magnitude larger than the signal we were looking for. So we came up with a sort of radiator design of the electrodes where you have the regions where the current is flowing in opposite directions, but where the electric potential is the same, so that they are equipotential. And here is shown a simulation of the voltage drop. Here is an X-spin picture of the actual device, and here is an experimental image of the voltage drop. Okay, and this, before I go into the details, I will give you a spoiler. Yes, in this case, we managed to measure spin accumulation, and this work has been published just last week, and it's open access. So I invite you to look at it at your own pace if you're interested. So I have mentioned that we are going to use a technique that is very surface sensitive. So it's important that the surface is clean, obviously. If not, we will only measure the surface dirt or oxide. And that we can check in the same microscope because it has an electron energy analyzer. We can do XPS, so X-ray photoemission microscopy, which is even more surface sensitive. In this case, we are talking about angstrom instead of nanometers. So if there is any surface oxidation at all, we will detect it humongously. And we see that after sputtering of the surface layer, in fact, the amount of surface oxidation is negligible. This is, for comparison, this is the spectrum, this red one, the bismuth 4F core level of a sample that has come directly from air. Okay, so it has the surface of the natural surface oxidation. And also, of course, before doing an experiment, you have to determine what is the maximum current you can apply before you blow up your electrodes, and more importantly in this case, or more subtly, at which temperature, which is already 90 or 100 C, so it's quite low, you start to have bismuth segregation to the surface or clumping or whatever. Then in this case, we don't have bismuth doped cobalt anymore. We have cobalt with inclusions of bismuth. It's not the same material, okay? What is the method we followed? Well, this is the X-ray absorption spectrum at the copper L edge. It has the L3 and L2 edges. This is the edge jump. And since these are very lengthy experiments, we did not measure the full spectrum for all the conditions, but we used a few selected energies, namely typically before the edge, at the edge, and after the edge. Okay, this is the typical. And in this case, it's very important to use also the off-edge data, because despite the best efforts, it's impossible to have zero background for measurements on different samples, different experimental runs, different days. So it's impossible to have exactly the same background. So I show an example here, 2 different samples on 2 different days with opposite currents. And for example, this is one set of measurements, no? The blue dots, tuck, 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 tuck. Each point itself is an average of 3 measurements, okay? So this takes a lot of statistics to be sure of things. And the red is another set, tuck, 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 tuck. So if you didn't have the off-peak energies where there is no dichroism, you wouldn't know what to do with this point. So you really need this normalization to be sure if you're going up or down, let's say, because the signals are very, very tiny, okay? So here is one full data set, for example. So, and you can see clearly that the signal that we are measuring, here in the order of -4, depends a lot on the current that we use, is clearly opposite for both edges, as it should be, for both absorption sub-edges, let's say. And also you can see here, this is one example where we did a few more energies instead of just pre-edge, but a few more. And you can see here that the shape of this spin accumulation signal, or of this, for the moment, XMCD signal, is the typical shape and position for spin accumulation at the Fermi level. So you see that the maximum of the signal is not at the maximum of the absorption edge, but slightly lower energy, so on the rising edge here. This is typical for transitions to the Fermi level, instead of to the center of the D levels, let's say. When we put together all the data sets, only then we could be sure that we were measuring something consistent, because they are again, very tiny signals. And then you can see clearly that across different thickness, samples, days, experimental runs, the signal is always inverted between L3 and L2, and it's also inverted when you change the current direction. The obtained induced magnetic moment is this one, 2.2 to the minus 12 per copper atom, which is of the same order of magnitude as the one measured for platinum, which is the, let's say, the standard spin hole material. And okay, we didn't independently determine the spin diffusion length, so I cannot give you a number for the spin hole angle, but I can give you curves that couple the spin diffusion length and the spin hole angle. And all our measurements are compatible with a spin diffusion length between 10 and 20 nanometers, which means that the value we are looking for is around 0.2, 0.25 spin hole angle. Other people call it 25% or 20%, but it's quite high. I mean, it's even higher than previously reported for the same material. Of course, we have a higher doping also, you have to think. The previous measurements were below 1% doping. So it's very promising. And in principle, one could determine the spin diffusion length doing systematic thickness-dependent studies, but with enough time, let's say. So that's all I wanted to tell you today. I have shown the first interface-free and element-selective detection of spin accumulation due to spin hole effect. The experiment was done by X-ray spectrum microscopy, specifically by photoemission electron microscopy. This is a method that is applicable to semiconductors, metals, ferromagnets, antiferromagnets. In this case, we use copper bismuth, and we show that it has a giant spin hole angle. We had to improve the device and method to minimize the background and increase the sensitivity. The first time is the most difficult, so this is work that is already done for you, if you want to do this experiment. And there are X-beams available at most synchrotron user facilities. So yeah, I encourage you to consider adding this method to your suite of detection techniques, because it's very pure. It's time-consuming, but let's say it's very directly addressing the element and without any interface. I have spoken on behalf of a large team, for whom I thank for their contributions. The most significant, Sandra Ruiz Gomez and Lucas Perez, who are in the audience, and Michael Forster, who is a beamline scientist at the X-beam at ALBA. And I thank you.